Hi, thanks everyone very much for having me. So I'm Matthew Feickert. I'm going to be talking very briefly a bit today about performing distributed statistical inference for particle physics with a library we use called pyhf that's powered by funcX. I'll very briefly note that this is the lightning talk version of a full talk that was given at SciPy 2021. So if you're interested in any of this, feel free to either click the link in the slides that will be uploaded later or reach out to us to get in contact. I first just want to take this opportunity to introduce the pyhf team and also the team that kind of worked on this. So the pyhf core development team consists of Lucas Heinrich, who's at CERN, myself, Matthew at the University of Illinois at Urbana-Champaign, and Jordan Stark, who's at UC Santa Cruz. We were also joined on this project by Ben Galuski, who's my colleague at Illinois over at NCSA, and I think who many of you know and love as one of the funcX developers. Okay, so as was mentioned, we're high-energy particle physicists, so we're interested in trying to go probe the universe for some of the fundamental structures and look for things like new particles, like dark matter, and also make better measurements about things that we know about, like the Higgs boson. But so when we're performing physics analysis at the Large Hadron Collider, pretty much anything that we want to do in terms of searching for new physics, making precision measurements about physics we already know about, and also trying to constrain the models that when we don't find new physics, trying to constrain our models through setting best limits. All of this requires building statistical models and fitting those models to data, which requires performing statistical inference. But for some of the really complex models, this traditionally has taken many hours, if not days, to actually perform. So a goal for pyhf is to try and empower analysts with fast fits and expressive models to try and reduce the time to insight and inference for these sorts of problems. So on slide 5, I'm just going to briefly mention that for the context of this talk, that pyhf is a pure Python library that's been developed in the high-energy physics domain for fitting multi-band statistical models, and we leverage different computational backends that can both take advantage of hardware acceleration as well as automatic differentiation, and that seems to work quite well. Just going to skip all the rest of this, but that's all that you need to know for this talk. So moving on. So traditionally, we've wanted to, in higher geophysics, and I think in many fields, there's this idea of using HPC facilities and just cluster computing to try and tackle large problems. And so we'd similarly like to try and leverage the resources that are abundant in higher geophysics in terms of HPC to be able to try and attack these problems as well, especially given the fact that for HPC systems that have hardware acceleration on them, so GPUs, then we can try and leverage pyhf's hardware accelerated backends to really attack these larger problems. And so what we'd like to, and given the kind of embarrassing parallel nature of some of these things, it would also be nice if we could try and attack this with a fitting as a function service. So we have partnered with Ben to try and see if we can actually do this by bringing funcX into the equation to try and see if we can make a fitting as a function style service on HPC systems. So in slide 8, the way that we have basically done this is, as I'm showing code that I think is familiar to many of you, we go ahead and first set up the funcX endpoint on the HPC system in question. And then we go ahead and define our user functions in terms of preparing a background model and then performing a hypothesis test that we want to perform, and we're going to be performing inference. So we go ahead and set up these user functions, and then we go ahead and, of course, register them with our local funcX client. And then once they're registered, we can go ahead and run these, so we can send them off, so we can to the funcX backend to run. And then while they're going and chugging away on our HPC systems, we can, of course, go ahead and query them on a regular basis with funcX get result to try and actually see if our tasks are done. And in terms of actually scaling these out, given the nature of the statistical inference problem that we're actually trying to perform, we can basically just scale this out across the backend to as many workers as can be handled, which and kind of given the nature of the statistical inferences that we're problems that we're doing, where for our physics scenarios, we're basically testing different different mass hypotheses for different particles. We can basically scale out this very efficiently so that we can run simultaneously across all the HPC workers we can have. And again, given all this, we've just been taking advantage of funcX's nice features that we've done this as a user by just writing very simple pure Python. And so the end result is, for our physics case that we care about, is we can go ahead and take a particular published physics analysis, and we can go ahead and get all 125 different signal models that were tested in this particular physics analysis that are published up on a data repository called hepdata in our field. And we can now use our pure Python script with funcX, where we can run in a total wall time of under 3 minutes. We can go ahead and have all of that data be downloaded from the hepdata archive. We can register all of the functions that we need. We can serialize all those functions and send them off to the funcX endpoint, execute all of them, and get all of our results back in just over 2 minutes and 30 seconds. Which means that so here we're reproducing a published analysis, the results from a published analysis, but this means that if we're now trying to use this as a function service for new analyses, that we could basically go from defining our signal hypotheses with our background only model to submitting jobs to actually starting to make plots that summarize our statistical inference just in a matter of minutes. And so at the moment, these studies were done when deploying to the University of Chicago's river cluster, but we're also doing some tests on NCSA Blue Waters, as well as looking at Exceed for using the GPUs there to take advantage of our hardware accelerated backends like JAX. And if you're interested in this, there's a little ASCII cinema here that you can watch to see the whole thing run by. Right, so a quick kind of comment and also question that I'll throw out there to people who are maybe more in the know than me is, since we're performing fitting functions as a service here, we aren't really able to, at least naively or easily as far as I know, take advantage of JIT compiling. And for some of the physics analyses and some of the simulations that we want to perform, we have a lot of pseudo experiment generation that would be really nice to be able to try and take advantage of JIT compilation. But this is a problem, as can be seen here on the right-hand side. JIT compilation can really speed up certain problems. For example, this is being shown using JAX. But to be able to leverage JIT functions, we need memory preserved across all invocations, and that's not something that I at least know how to do with funcX, given the nature of the distributed problem. So if you have any ideas on how to maybe make this more of a magic bullet, or how to try and sidestep some of these problems, be really interested in hearing from you. But with that, I'll just kind of close up with the summary that through using these pure Python libraries of pyhf and then funcX, we were able to parallelize and accelerate a statistical inference problem from the field of particle physics and be able to deploy this pretty transparently and easily. And I'm definitely not a funcX expert, but just after a little bit of work, reading the docs and talking with Ben, we were able to deploy this solution pretty easily. So thanks very much for your time, and I'm happy to try and take any questions in like the minute or so that I have left.
Cool. So thanks for that. If you've got questions, put them in the chat. I'll give Dante a heads up. You're up next, Dante. So I've got a question. You talked about fitting functions as a service. So that makes me think that you potentially would be offering this to some users, I guess, who are physicists. What's the input that they would be putting into this fitting functions as a service? Is it a large data set, or is it funcX code or Python code, or what?
Yeah, so the short answer is we are this is something that we're trying to think about more on how to actually try and maybe with different existing efforts such as IRIS-HEP, the Institute for Research and Innovation in Software for High Energy Physics, in which myself, Dan Katz, and Ben are all members of. We're thinking about trying to how to actually set things up like this, but the short answer to your question is, what would people actually be submitting? They would be submitting basically just JSON, which would contain basically the full declarative specification of the statistical model that they want to fit. And then they, in this view, they would submit JSON that they could just post, and then on the back end in a fitting as a service analysis facility, we would basically take that and be able to deploy that as needed.
Cool. All right. Anyone else have any questions? If not, we will move on to Dante, who is
probably not a question so much, but I'd love to chat more about the JIT stuff, Matthew. I think that's super interesting, and I think that certainly shared memory stuff is doable. JIT, we probably should think about. So maybe an offline chat about JIT. Anyone that's interested.
Yeah, I've had some thoughts about that as well.